Okay, there's a third solution to this problem of crossed aldols, and that is to use the Mukaiyama Aldol reaction, which is really just a variation of the normal aldol reaction, where you use a silicon enolate. And the silicon enolate can actually be isolated, unlike the lithium enolate that you have to kind of make it and use it straight away. These can be actually isolated and then reacted with an aldehyde or ketone in the presence of a Lewis acid. Most often it's done with titanium tetrachloride, which is a fairly nasty corrosive liquid, but it's fairly cheap. You can use other Lewis acids like boron trifluoride etherate. So let's look at a couple of examples of the Mukaiyama Aldol. You can use this silicon enolate, and incidentally this is just made from acetophenone, which is a very common Friedel Crafts product that you may have seen. And that silicon enolate will react with acetone in the presence of our titanium tetrachloride. And we get the aldol addition product. So this is quite a useful one. That's 74% yield. Another example. You can make a silicon enolate from cyclohexanone, and that will react with an aldehyde. Now, this is an example that, in fact, you could do using the conditions I described earlier, just a simple base, but it does show how the aldehydes do work with the Mukaiyama as well. So those are three ways we can do crossed aldol chemistry. Next, I would like to cover the stereoselective or asymmetric version of the aldol reaction, which most often would be done using Evans oxazolidinone as a chiral auxiliary. And we'll cover that next, and I'd like you to read over that section in the textbook.